All right, this is AP Chemistry Notes, pages 86 through 88. And this one should be fairly interesting. We are going to analyze what is going on when a battery works. And we're going to keep it pretty simple, but you should have a decent understanding of what's going on with when a battery is operating and how does it produce electricity that we use, like in your cell phone or remote control, or when you start your car and the battery fires up the engine, or for example, in the laptop I'm using right now if it's not plugged in. And a fancy name for a battery is an electrochemical cell. So you've got some chemical stuff happening, which produces electricity. Now, a couple of terms to be aware of is voltaic and galvanic. Both of these terms refer to a battery being a battery. In other words, it is producing electricity. So again, voltaic and galvanic. Galvanic is named after a person. Actually, they both are. Galvanic, I think his name was Louis Galvani, and voltaic after Alessandro Volta, which of course we have the unit volts as well from him. Electrochemical cell is more generic. That just means it is a battery. It's not saying whether it's producing electricity or it could be recharged, in which it's absorbing electricity. So that's a generic term, whereas voltaic and galvanic mean spontaneous. The reaction is occurring on its own and it's producing electricity. This term harness, sorry, it's a little blurry, the flow of electricity is basically what we do. We allow the electricity to run through the battery, but instead of allowing it to run directly from one pole of the battery to the other pole of the battery, we put some sort of electronic device between the poles. And as the electrons, which is the electricity, as it runs through the device, it powers the device. So we kind of, I guess you could say that we kind of hijack the battery a little bit and put our device in its path. So it has no choice but to go through our device. All right, let's get to some of the parts. You've got something called the cathode. It's called the cathode because there will be cations migrating or moving towards it. That doesn't mean they touch it, they just go towards it. As they do this, they consume electrons. And so, in other words, they gain electrons. And so this is where reduction will happen. There's another thing called the anode. This refers to anions migrate or move towards it. Again, they don't necessarily touch it. They might touch it, they might not, but they do move towards it and they give off electrons. And to give off electrons is, of course, oxidation. And a way to keep this straight is that you have consonants here and vowels here. So reduction, cathode, oxidation, anode. And these are typically the two poles of the battery, so the positive and negative pole. I don't want to get into which one's positive and which one's negative. That gets a little tricky because often neither of them are positive or negative. And when one is positive or negative, it depends on what direction you're running the battery, whether you're charging it or whether you're allowing it to run. And that gets a little bit more complicated than what I want to do in this lesson. Now, another component is called the salt bridge, and we'll get into that once we get to the first picture. This is the symbol. It's like two vertical lines. You'll often see a reaction written where you've got some sort of chemical symbols, and then you'll see these two lines, and then you'll see more chemical symbols. And the two lines represent the salt bridge. Here are two common salt bridge chemicals, especially the potassium nitrate, because it doesn't react with anything in the battery because you don't want unintended reactions occurring because that could cause the battery to not function or to fail. And it allows the flow of current, other things that I'll explain when we get to the picture. And the electrodes are the actual things on opposite ends of the battery. So if you think of a typical battery, you've got something here, looks like a I'm drawing what would be like a D battery, and you've got the positive end, and this would be the typically labeled the positive, and this would be the negative end. Electrodes refer to the two ends, and traditionally they will be metals. You'll have a certain metal on this end and a different metal on this end. Now, they don't have to be metals. So if they are metals, you use the corresponding metal. Now, at this point, you should be thinking corresponding to what? Corresponding to the half reaction. So if your half reaction, like down below, involves zinc, you will use a zinc electrode. If your half reaction involves copper, you'll use a copper electrode. Oh, wait a second. I think I have a copper pin. I think that, oh, I have to use that. I actually have a copper pin today. I think I have a zinc pin too. Well, not zinc, but it's silver looking. Let's go. That's close enough to what zinc would look like. So let's go with that. So we're going to use some fancy pins for this lesson since I can. So let's do that again. The zinc electrode would be made of zinc, and the copper electrode would be made of copper. Oh, that's better. Now the question comes up, what if your electrode is a non-metal? There's no such thing as a metal chlorine electrode. In this case, you usually use an inert or non-reactive electrode just to help the electrons flow. Platinum is a great choice, however expensive. A nickel chromium alloy is another common one, and graphite is also useful depending on the particular battery. And actually, the traditional battery that we're all familiar with, actually one of its electrodes is a graphite electrode. So what I want to do now is look at a classic example of what a battery would look like. And in this case, we're going to look at, and I want to see the whole thing at once. It should be good enough right there. I don't want to make things too small. I don't need that line. Let's do that. So, as I mentioned in my writing here, you should memorize this one. Just memorize this reaction. You saw it in the last lesson. I didn't make a big deal out of it. I use it as my example, but it's just a classic reaction. It's nice to have in your toolbox of things to work with. And memorize what's happening in this drawing, because then you can just refer back to this drawing and you can compare to it. So just like we split a reaction into half reactions, this has been split into what are called half cells. So you can think of this as one half cell, and this as the other half cell, where each half reaction occurs. Now, you don't have to separate them like this, but this is the best way to start. So let's analyze what reaction is happening, and then we can figure out why does this actually produce electricity that can be used. And we'll also explain the salt bridge, which is this very awkward looking tube in the middle. Let's start on the left. So as you can see from the reaction, the zinc is going from neutral solid to aqueous ion. So the half reaction looks like this. Here. The zinc solid is losing 2 electrons to become an ion that dissolves. So I drew that in the picture here. This would be let me use the zinc color, a solid zinc electrode. So it'd be a chunk of zinc metal. And as it reacts, it turns +2 ion, which dissolves into the solution. This is one reason why the battery eventually stops working. You run out of metal zinc. It's all become a +2 ion and can't do the reaction anymore. So that's one reason why a battery might stop working. Now this is called the anode because oxidation is occurring. And I said it gets smaller. It actually physically gets smaller. We'll talk about rechargeable things later. Now what it does is as it does this reaction is it sends electrons up the wire. So electrons go up this wire, they carry on, they go to whatever devices we're powering. In this case, it's a old-fashioned looking light bulb, which to be this reaction, the zinc copper reaction, would not power a classic filament light bulb like this picture shows. They might power some really tiny light bulb or an LED, but this picture makes it look like it's the kind of light bulb that you'd plug into a socket and it wouldn't power this. But let's just play along and say that the electrons go through, they wiggle through here, light's produced. That's not today's discussion. And they keep going. They don't stop. Electrons keep moving along and they go down here. They have to go somewhere. You can't just send them to the light bulb and leave them there. So we need the opposite reaction to happen on this other half. So now let's look at the copper half. So what's happening here, as labeled above, is we have copper +2 ions that are in solution, gaining electrons to become copper metal. And I have that here. Copper ions gaining electrons to become copper metal. This is reduction, and this is called the cathode, because reduction happens at the cathode. Now this electrode, if you were to look at it, would again look like copper. You would see a chunk of copper in there. And this electrode would get bigger because we have copper ions gaining electrons and becoming copper metal. So you'd see this thing grow, not a lot, but a little bit. In this case, it would be roughly equal to the amount that the zinc electrode gets smaller. Now, we've shown the two half equations here and here. We've shown the movement of the electrons, roughly. Let me emphasize this. From this side over to this side through the wire. I don't want to keep that massive pin. If we didn't have the salt bridge, so for example, if this was not here, nothing would happen. You'd have these two containers of solutions with their electrodes. You'd have this wire and this bulb. And again, let's pretend the bulb would actually work. But nothing would happen because you don't have a complete circuit. In order to have electricity work, you have to have a circuit. For example, you have to have a battery connected to some sort of device connected back to the battery. If this is broken, then you don't have a circuit. Circuit means circle, so you have to have a full circle. If we don't have that, we don't have the full circle. Now, things have gotten very messy, so let me clean this whole page up here. So it'll give me a chance to use my, my fancy copper and zinc pen again. So focusing on the salt bridge, the first thing the salt bridge does is it connects and completes the circuit. So now if I were to follow this with my highlighter, see if I have a good highlighter color for this. Not really, I'll stick to the normal one. The electrons start here, they go up the wire, They do their thing in the device. They go down to this electrode here. But we do need a connection here as well to keep the circuit. So let me tidy a couple things up here. I've got too many things running in my computer. It's getting upset. I can tell because things are going slow suddenly. Let's go back here. What the salt bridge does secondly is, if it weren't for the salt bridge, these zinc ions would build up a positive charge over here, and that positive charge would prevent the release of electrons. Likewise, in the other half, we would be losing positive ions. We'd have copper ions that would be losing to the electrode, and that would make this side negative. And so we'd get a buildup of negative charges over here, and that would prevent the electrons from moving into this side. It's called polarization. It would stop the battery from working very quickly, if at all. So we need something to counteract the buildup of positives on this side, the left, the way I've drawn it, and negatives on this side, the right. Well, that's what the salt bridge does. It has a salt in it. In this particular drawing, whoever made it, they put potassium sulfate, which is fine. And so what happens is, every time a zinc +2 ion pops off this electrode over here, what happens is a sulfate ion dumps out to counteract it and keep it from getting an overall charge. Likewise, on the right half, every time a copper goes to the electrode, we have some potassium. It'd take 2 potassiums, dump out of this side of the salt bridge to counteract that and replace those positives, and that keeps the battery running. Now, that's another reason the battery might eventually stop running, is you might run out of ions in the salt bridge, or maybe it just gets saturated, one of the sides or something like that. So there's a variety of reasons why the battery might stop working, and that's why a lot of work is putting into the technology of making better batteries. Again, I recommend you memorize this system. Learn this reaction here and memorize. You don't need to memorize this exact picture, but memorize what's happening, and you can just relate any future issues to this one. Let's look at a different way of doing this. By the way, I make a note here, I'm just now seeing it, about the negative and positive labels. We don't want to get into that right now. That gets a little messy. Okay, here's a new picture with a new reaction. Where is the reaction? Oh, it's way down there. Let's look at the reaction, and then I'm going to zoom back in up there. So it's going to get too messy and too small for you to see. So in this case, we're going to do a slightly different reaction. This time we still have zinc doing the same thing, but instead of copper, we have, this is in an acid, so we have H plus gaining electrons to become hydrogen gas. And one way you might see this written is you might see it labeled this way right here, where we've got the zinc half, the hydrogen half, and then this thing in the middle represents the salt bridge between them. And notice that PT, that means platinum, because there's no such thing as a hydrogen electrode, so you have to use something else, and you use a platinum electrode if you can afford it. So now looking here at the picture, that's good enough right there. The zinc side over here is the same. So we've got a zinc electrode, same reaction as before. Oxidation again, producing zinc ions. The platinum side, or the, excuse me, I shouldn't say the platinum side, the hydrogen side, we have hydrogen ions gaining electrons to make hydrogen gas. A platinum electrode, I want you to ignore this. This right here has to do with the way the electrode works. It would only cause problems for us right now. So don't even look at that. I should just get it out of our notes. I think it just causes confusion. And notice, hydrogen is a gas. So as this reaction occurs, you get these bubbles bubbling out of the solution of hydrogen gas. That would actually happen. You would see this. Let's see, oxidation on the left, anode, reduction on the right, cathode, those are just terms. And in this case, it has it going through a little meter. So the electrons are going the same direction from left to right, and they would just give us some sort of indication here that we're getting electricity flowing in this meter. And that would be more likely to happen. You would actually see this with a meter, as opposed to the last example with it lighting up that old school light bulb, which wouldn't really work very well. Now, instead of a salt bridge, this time we got a little more sophisticated, and they put what says a porous partition. In other words, like a semi-permeable membrane all the way down the middle that keeps us as two halves. We have a left half and a right half. And also, this would make things more compact and reasonable. Rather than having two separate jars of liquid, which would be very inconvenient, you can package this into a single item and stick it in an item like your cell phone. So this is more practical. In this case, to help deal with the buildup of positives over here and the loss of positives on the right, which would eventually make the solution negative, what this one can do is it can just take sulfate, for example, and it can send it from the right side to the left side through the porous partition. And that would help solve both problems. You'd be taking negatives away from the right, and you'd be putting negatives on the left. Our anode would still get smaller. Our cathode wouldn't get bigger like the copper one did, but we would see the formation of those hydrogen bubbles. Now what I want to do is go backwards. Now, if you go backwards, notice this is a non-spontaneous reaction in which we have to put electricity in. Now, the term for this would be electrolysis or electrolytic. So it's still an electrochemical cell, but we're going the other direction. Or you could say we are recharging the battery. Now, some batteries are rechargeable because of the technology and reactions that are involved, and other ones aren't rechargeable. Part of it has to do with the cost of the materials, and part of it has to do with just convenience. But again, if it's rechargeable and we are recharging, these are two terms that can be used for that, electrolytic or electrolysis. The other one was voltaic and galvanic. Now, in this case, you got to put power into this, charge it. For this example, we're doing the opposite of this voltaic cell, the regular battery on page 86. So if I go back to page 86, we're doing the opposite of this reaction right here. So you'll see in this case, we're losing zinc and making copper. If I go to the current one, if you look at the reaction, we are making zinc and we are losing copper. So we're taking that same system and we're running it the opposite way. Notice the electrons are now going the opposite way. There. I mentioned that we need a power source greater than 1.10 volts. I'm going to just let you simmer on that. There's a reason. And I want you to think about that 1.10 volts. And why does it have to be more than 1.10 volts? Just let that rest in your brain and we'll go through that in a couple lessons as to why that is the case. We're not quite ready for that. So if we analyze the reactions, we've got the zinc on the left again, copper on the right. Oh, I'm using the wrong pins. I got to use the right pins. Zinc on the left, copper on the right. But this time, since the reactions are opposite, the zinc ions are going towards the electrode and making zinc metal, and this electrode gets bigger, it regains what it lost earlier, and the copper leaves the electrode to go into solution. Copper solid becomes copper aqueous, and that copper electrode that was getting bigger earlier now will start to get smaller and go back to how it used to be. Similar to the last example, we had sulfate moving to the left. Now we'll have sulfate moving to the right if we keep that same system. Sulfate isn't made of copper. I should use a different color. There we go. This is an example. It says 1 molar zinc and 1 molar copper. It doesn't have to be that. That would just be one example. The main thing here is just that the reaction's going backwards. What happens to the electrodes is the opposite, and the terms that are used to describe this. And this is recharging a battery. I mentioned down here, why must the power be higher than 1.10 volts? Like I said, I want you to think about it. See if you can come up with it on your own. Don't necessarily look it up, just think about it. And think about what you already know about reactions and why certain reactions go in one direction or why they might go in the other direction. And that should take care of this lesson.